is equal to load over the original cross-sectional area, and strain is equal to that change in length over the original. And having that, having that data, from that data, I can plot plot those points, and this does not look linear. Where this is now stress, and that's now strain. And in my mind, the only thing that tends to go wrong at this step, if you do it this way, is in your calculation of stress. So typically, when you calculate stress, you're going to have newtons per centimeter squared. And that's not an appropriate unit if I want to calculate modulus down the road. I need that, the y-axis to be in megapascals. So step by step, I would multiply by 100, sorry, 100 squared, 10 to the 4th centimeters per meter squared. And then these are now pascals. I need megapascals, so I divide by 10 to the 6. And now my answer, my units for stress are in megapascals. As long as you do that, so that this is really megapascals, then your slope will be modular. You will be able to calculate modulus from the slope. And if you do it this way, once you have done this, then the maximum value, whatever it is, of stress, that's ultimate tensile strength. You can go straight onto this strain graph, look for the point where strain is 0.002, draw a line that's parallel, and wherever it crosses, that is your yield strength. And I think some people have this question in their mind of why is she choosing 0.002 and not asking that question. It's just convention. It's how yield strength is defined. Yield strength is defined as the stress level at which you have 0.2% or 0.002 strain, permanent strain. That's it. That's just the definition of yield strength. So again, if you've converted your load and your extension to stress strength and on the curve, you can just use the curve straight to get your answer for ultimate tensile strength and yield strength. You can also use it directly to calculate modulus. It's just the change in stress over the change in strain. And the change in stress should be in megapascals. Strain doesn't have any units. So if you use this method, you've got your original load deformation curve, you're turning that into a table, you're calculating stress and strain, and then you're plotting stress and strain to get your values. If instead, you have to figure out how to get rid of this every single time. That's not the point.
Professor?
Yeah.
So I take it most people are going to be going to test Friday?
Yes, I think there's just one person who's taking the test on Tuesday.
Okay. So most people are going to be at class on Tuesday?
Yeah, we're having class rate as regular on Tuesday.
Oh,
Class-
you're right.
It would be a regular class on Tuesday.
Oh, okay.
We're doing kind of what we would have done, sort of, on Friday. But yeah, we'll have a regular class on Tuesday.
Oh, okay. All right. Thank you.
Sure. Okay, now, what I just showed you might be the most straightforward method, but it wouldn't be the fastest method, and it wouldn't be it would be open to more error just because there's more times where you're making estimates or you're rounding or whatever. And so the alternative here is if you have a load extension curve, I know that the highest point for load, I can see that on the graph. If I just divide that by the original cross-sectional areas, I don't even need to make a table. I just take that highest point, and granted you have to be able to read that on your graph. Take that highest value of load, divide it by the original area, that's ultimate tensile strength. I can take 2 points in the linear region, and this would be delta L1 and load 1 and delta L2 load 2, X and Y. Modulus is going to be equal to the change in stress or the change in the strain in the linear region, which would be the same as the change in load over the original area divided by the change in length over the original length. Change in length over the original length, that's change in strain. change in load over the original area, that's change in stress. So modulus could easily be, in this case, load 1 minus load 2 over delta L 1 minus delta L 2. That's the change in load over the change in length. And then just multiply that by L0 over A0. So this change in load, that'll be in terms of newtons. The original length would be in terms of millimeters or centimeters. Let's say it's in centimeters. Original area would be in centimeters squared, and the change in length would be in centimeters. So my units end up being, again, newtons per square centimeter. And units for E, for modulus, should be in gigapascals. So whatever you get in newtons per square centimeter, you're going to take that times 10 to the 4 to get into the pascals, and then you're going to divide it by 10 to the 6 to get into, oops, that's not right, 10 to the 9 to get into gigapascals. So now, I have not had to do any reading data off a graph, putting it in a table, recalculating and plotting a new graph. And I have ultimate tensile strength and I have modulus. Just duplicate. Okay, so I'm just going to clear away some of this. Okay. So the yield strength is measured at 0.2% strain or 0.002 strain. So I need to know where on this delta L, on this x-axis, where is 0.002 strain? And I know that strain is the change in length over the original length. And I will be given the original length and strain will be 0.002. Which means I'm going to be looking for where delta L is equal to, I can solve for delta L here as being equal to L0 times 0.002, right? And like I said, L0 is given, so you can calculate that value. And then you go on the delta L axis and you find that value, wherever it is, you mark it on your x-axis. And then you do just like you would if this was a stress breaker. Draw a line with the same slope. And determine where, at what load does that cross. So that might be like, I guess, P for load, P sub y, rather than stress, rather than sigma sub y. But sigma sub y is just this load over the original area. And once you have that load and you're given the original area, you can solve for yield strength. And again, you didn't need to draw a new graph, and you didn't need to take points off of this graph. All right? Either way is fine. You can do it any way you want. You will have a load deformation curve. You will have graph paper if you want it. You will have a table set up if you want to use that. And your goal is to calculate those three measurements: ultimate tensile strength, yield strength, and modulus. All right? So that's our mechanical property calculations. Now, make sure that you look at your notes for the meaning, the measurement of ductility and toughness and hardness. And for hardness, we had the Brinell and the Rockwell scales. All right. Okay, so that's mechanical properties. After we did mechanical properties, then we did crystal structures, and ultimately we found an equation for theoretical density. I'm not going to derive these equations again. Look back in your notes. But you will want to be able to calculate one of density, atomic radius, atomic mass, and crystal structure. Given the other three. And I'll give you that equation that has the xy cubed in it. So density is at xy cubed, that's a function of crystal structure, times the atomic atomic weight or atomic mass. So that's got units of atoms, and this is gonna be grams per mole, so I need to have Avogadro's number in moles per gram. Let's see, atoms, atomic weight is grams per mole, and then I have atoms a mole are the units for Avogadro's number. So now I've got atoms cancel and moles cancel. I've got grams. I need to have the volume here. The volume of the unit cell is A cubed, which is, let me think here, X. No, that's not volume. A cubed is Y times R cubed. Is that right? Sorry, I need to write it up the way I normally do. So Y A is equal to 4R. There we go. So A is equal to 4R over Y. Of course, these equations are on your equation sheet. So I've got my X and Y cubed already, so I'm gonna need 64, that's 4 cubed, and R cubed. Now you're gonna have conversion factors in here so that you get units of density in grams per centimeter cubed. So for example, R might be in picometers, and you have to convert that to centimeters in this equation. All right. That will be calculating a theoretical density. And as far as crystal structure goes, that I'm not going to ask you for to calculate atomic packing factor. There's plenty of other things to ask you to calculate. So for crystal structure, this is really the only calculation, but recognize there's 4 different ways to write that equation depending on what the unknown is.
So the A term represents that XY cubed, correct?
No. A is the length of the side, so A cubed is the volume. And then there's a relationship between A and radius depending on the crystal structure, and that's where Y comes in. So here, A is 4R over Y, and Y is either square root of 2 or square root of 3, depending on the crystal structure, but you can just leave it like that. X is not part of A.
Okay. So I guess we could have a question that asks for the volume of a cell and do A cubed to find that, correct?
Right, if I ask that, yes, A cubed is the volume of a cell, yes.
Thank you.
Uh-huh. Okay. So that took, so then we did mechanical properties, and then we did crystal structure, the structure of metals. And then we moved from there to defects, because the theoretical density assumes atoms in every location, in every lattice location, maybe that's better. So when we calculate theoretical density, it's like we're assuming there's one crystal, and the atoms are in a certain arrangement with respect to regular space, and they're moving according to the crystal structure in X and Y and Z direction. And there's no interruption, and there's nothing missing. And so the density is going to be higher because of that assumption. In reality, because there are defects, and in this case, vacancies, the experimental density is going to be lower. One of the reasons we know there are crystal defects is because of that, is because the measured density is always less than what we would predict. And so that takes us to talking about defects. And so I went through just generally
Do you want me to answer?
a discussion
No, the
of
second
the,
second
or
one.
naming, let's say, naming of
That was
the,
actually BCC one.
It was FCC.
three kinds of
It's
defects.
a transitional metal. Transitional metals are always BCC. She had it flipped, so the
There's
percent-
one
percent
dimensional or
mass
point
or whatever it
defects.
was, it calculated out to an FCC, but molybdenum is a transition metal in the periodic table.
Either vacancies
Oh,
or impurities.
I got full credit for it, so I explained it.
Yeah.
And then there are line defects.
I mean, as long as you explain it inside of the test, I think she won't mind. Who knows?
And those are dislocations.
Just confused the hell out of me.
And then there are surface defects. And those are grain boundaries. And the impurities and the dislocations and the grain boundaries strengthen metals by obstructing dislocation motion. All of them.
All right.
Was that you or was that?
I don't know. Is the class still going?
I think that was you.
Yeah, probably.
So that means that, okay, now let's focus just on point defects. And so that was, looking at vacancies.
Your settings are right.
And impurities.
Your settings are right. You just have to make a full screen. That's about it.
And vacancy, a vacancy is a place where there should be an atom and there isn't an atom, and there are more of those as
Your computer's
metal
about to
heats
die.
up.
Your computer's just about to die.
So, the number increases with temperature.
Alright.
According
Ah, 32.
to the equation, number of vacancies equals number of places of, there's an atom, e to the negative q sub b over k t. So here's temperature. As temperature goes up, this number gets smaller. It's a negative exponent. So that means that the value gets bigger because the negative exponent is getting smaller. And n, the number of atom locations per cubic meter is just the density, which is the grams per cubic centimeter, converted that to grams per cubic meter, use atomic mass to make that into, and Avogadro's number, to make that into atoms per cubic meter. So I've got density, which is in grams per centimeter cubed, times, let's see, I need to divide by atomic mass in grams per mole. And that gets rid of grams, and then up here I need to have Avogadro's number of atoms per mole. That gets rid of moles, so now I have atoms per cubic centimeter, and I need to turn that into atoms per cubic meter. So I know that there's 100 centimeters. Let's see, I need to put that in the numerator. Now I've got grams. Let's see. Grams have canceled. Moles have canceled. Cubic centimeters have canceled. And I've got atoms per cubic meter. So that's N. And the only other thing to make sure you know how to do is just dealing with exponents on your calculator. Okay, so then impurity, the other kind of defect, could be interstitial. Those are the ones that are in between atoms, or substitutional. They take up the place of an atom. And since they take up a place of an atom, they can't move into a material unless there are vacancies for them to move into, so. In order for diffusion of substitutional impurity, we need to have vacancies in order for the substitutional impurities to fuse. And then we had solubility rules. That determine which metals can be substitutional impurities into which other metals. So which metals can be solutes in a given metal solvent. And those rules, those are called the Hume-Rothery rules. You don't need to remember that. But they include a limitation as far as atomic radius difference, and crystal structure difference, and valence difference. So once you know which metals can diffuse into which other metals, then we can use our diffusion equations to talk about how fast that would happen. Derived the equation for steady state diffusion, and I said at the time, and I still mean it, that it's kind of good to know that equation, but it's rare that that you see steady state in materials, and it's just too basic, I think, for us to bother with making calculations. And so we did it. I presented Fick's first law, the law of steady state, but you don't need to remember that equation or to use that. And then we went, last topic for this exam, we talked about the relationship between diffusivity into temperature. And so the general equation was D is equal to D0, E to the minus Q over RT. This is a different Q, and notice that we have R, the gas constant, rather than K, Boltzmann's constant. D0 and Q are constant for each specific solute solvent. So there's a value for D0 and Q for carbon and iron, which we've been using for carburization, but all pairs have their own unique their own unique values for Q and D0. And this equation says, okay, we have these things that are constant for a pair. How does that vary with temperature? That's what this equation tells you. So there can be questions that involve solving for one unknown. From that equation. And typically that's going to be D or temperature T. If you're solving for D, you can just use that equation as given. Because you're given Q and D0. If you're solving for temperature, then you probably will be better off rewriting this equation so that you take temperature out of the exponent term. So just use that formal equation to solve for D, given Q and D0 and T, and write the equation like this, form the logarithmic form if you need to solve for T, given Q and D naught and D. And then the last problem type with the diffusion, and again, this doesn't matter if it's steady state or not.
Could we do a type 1 problem for the diffusivity?
Sure. Might need to look up some values here, but I have a book right here. So. Let's see. If we wanted to find, I think in class I did one where we're solving for D, so let's do one where we're solving for T. Let's see what I got here. For zinc, diffusing in copper, E0 is 2.4 times 10 to the negative 5 meters squared per second, and Q is equal to 189 kilojoules per mole. At what temperature will D be equal to, you know, if I make up the number, see if I can. 5 times 10 to the negative 18 meters squared per second. Okay, so my unknown is temperature. So I want to write this equation in that logarithmic form and say that natural log of D, which is 5 times 10 to the negative 18, is equal to the natural log of D0, 2.4 times 10 to the negative 5, minus Q, 189,000 over RT, 8.31 times T. Where is my calculator? Okay, so 5 times 10, -18. So this is -39.8. 2.4 times 10. 5. -10.6 minus 189,000 over 8.31 times T. So 39.8, 7.6, so -29.2 is equal to -189,000 over 8.31 times T. So that means T is going to be equal to 189,000 over 8.31 times 29.2. So that's 779, and remember now that that's in Kelvin. So you would subtract 273 to get it into degree C. So it would be 506 degrees C. Does that help? Okay. So lastly, the last version of that problem would be where I'm solving typically type 2 problem would be typically for finding E0 and Q. So we're given D and T at at 2 different temperatures.
Wait, can we do the type 1 problem?
That's what I just did.
Oh, okay, then never mind, sorry.
That's all right. That's right. Let's see.
Sorry, I thought we were, the type 1 problem is like with everything, like finding Z and stuff.
Oh, so yeah, we had type 1 and type 2 problems for non-steady state, but that's not on the test.
Oh, okay, that's what I was worried about, thank you.
Yeah, no. The topics end with, let's see, what's coming up is Monday. So the topics end with last Monday's class. So, D versus temperature. But there's nothing with error function on this test.
Okay, that's sweet, thank you.
Yeah, here. All right, so this is the other kind of question for finding relationships between diffusivity and temperature. And in this case, we have 2 unknowns. which means we have two equations, we need two equations. So, what you'll do is for your two different, let's say I've got E1 at T1 and E2 at T2, and you want to make sure that these are in Kelvin. We would write two equations, natural log of D1 equals the natural log of D0, which is a constant, minus Q over R T1, and natural log of D2 is natural log of D0 minus Q over R T2. And you would subtract one of the equations from the other. What that will do is get rid of D0. So I've got natural log of D1 minus the natural log of D2 is equal to Q over R. I gotta get the signs here. Negative Q over R times T1, 1 over T1 minus 1 over T2. I think that's right. Yeah. So then you solve for Q. Then substitute Q into one of the original equations. To find B0. And then if you're asked to find D at a third temperature, you'll just use Q and D0 to do that. So the homework for that is what's due on Tuesday, right? Or is that the homework we just turned in? No, yeah, that's the homework. I believe that's the homework that's due on, no, the homework that's due on Tuesday was non-steady state. So you had a homework, the solution is posted, and you've got it back, that has these kinds of problems on it. All right, any questions? I don't know what just happened. Do you still hear me? Yeah, okay. Something funny happened with the screen here on my computer. Any other questions? Okay, well, we will have class on Tuesday. We'll be doing more non-steady state diffusion. I have office hours from 12:30 to 2 on Tuesday in the classroom where we meet. And then I'll also have hours on Wednesday at 2 o'clock in the Learning Commons by the coffee shop. If other questions come to you in between now and then and the exam. And then the exam will be Friday. We'll have maybe 45 minutes of lecture. And then the last bit of the time will be for the exam. And like we've said before, the last 15 minutes that you spend on your exam will be, am I going to upload this to a PowerPoint? It is a PowerPoint, and I will post it on Blackboard. I think that's your question, Chris. And that's part of the reason for doing this online is that we do have a recording. Now, you don't have my voice recording, you'll have these slides. Okay, any questions? Let's make sure there aren't any other. Let's see. Yep, that's it for the questions. Okay, nothing new here. I mean, this is all just like what we've done in class, but it's a good rehearsal. Tim, let's plan on 7 o'clock on Tuesday. It's just you, so that'll work.
Sounds good.
Okay. So that's it. I hope you have a good rest of your Sunday, and I'll see you on Tuesday.